we introduce InterPreT, an interactive framework that learns symbolic predicates from language feedback for generalizable task planning. I'm Muzhi from UCLA, and my collaborators are Yifeng Zhu, Song-Chun Zhu, Ying Nian, and Yuke. This work is a joint effort by UCLA and UT Austin. Many household tasks, such as cooking spaghetti, require robots to plan a long sequence of actions. This problem is known as task planning. Traditionally, task planning relies on a symbolic planning domain defined in PDDL, Planning Domain Definition Language. A PDDL domain consists of predicates that define important symbolic relations and operators that describe action preconditions and effects. Notably, each predicate is associated with a binary-valued predicate function that classifies the relation holds or not given raw observations. While PDDL-based planning is effective, it's usually non-trivial to handcraft predicates and operators even for human experts. Then how can robots learn predicates for planning? Human infants can quickly learn spatial concepts from caregivers' language feedback during physical play. Inspired by this, we propose to learn predicates from language feedback during embodied interaction. As the robot interacts with the environment with primitive actions, we have a non-expert human give language feedback that provides information on task goals and action feasibility. InterPreT learns predicates and operators on the fly, which are then used by a PDDL planner to generate plans for further interaction. The pipeline of InterPreT starts from leveraging GPT-4, a pre-trained large language model to process language feedback. We identify the predicates to learn, extract predicate labels, and reason action preconditions. Then for each identified predicate, we generate its predicate function in Python using the prior knowledge of GPT-4 by composing low-level perception APIs with logical structures and arithmetic operations. We assume a known set of perception APIs that provide basic visual understanding abilities such as object detection and segmentation. Then such predicate functions can directly parse raw observations into symbolic states. We further iteratively correct the predicate functions with GPT-4 to align their predictions to the extracted predicate labels. This mechanism allows closed-loop predicate learning from language feedback. With the learned predicates, we also learn operators from interaction data using a cluster-then-search algorithm. To evaluate InterPreT, we design a suite of simulated and real-world robot manipulation domains that feature different task semantics and constraints. In particular, we want to evaluate how well the learned predicates and operators can generalize to uncertain tasks with more objects, novel goals, and a combination of both. In simulated domains, we compare InterPreT with two LLM-based baselines, inner monologue and code as policies. InterPreT shows remarkable generalization ability. On the most challenging test sets, it achieves 73% success rate and outperforms all baselines by a large margin. In real-world domains, InterPreT solves 40% of the most complex tasks on average, while the baseline fails completely. The learned predicates and operators enable InterPreT to solve challenging tasks, including stacking multiple objects on a receptacle and preparing a breakfast table. If you want to learn more about our work, please refer to our project page. Please feel free to drop me an email if you have any questions about InterPreT. Thank you so much for your attention.